G'day. Copy the heading down and then we'll do some hard yakka. In our last video, you constructed a table showing the most common element and radical formulas. Try to commit that table to memory by the end of Year 10. To help you, we will start with a quick quiz of 10 questions. Write the names and formulas for each, given the clues. Number 1. The reactive metal found in common salt. Two, a brown metal used in electric wiring. Three, the gas that supports burning. 4. This nonmetal that was once called brimstone. 5. This metal alloyed with copper to form bronze. 6. This poisonous metal used by the Romans for plumbing. 7. This radical found in strong alkalis. 8. This nonmetal used as an antiseptic. 9. This important nonmetal of life. 10. This metal that burns with a white hot flame. Now write down these simplified rules for writing chemical formulas. we will begin the hard stuff by writing the formulas for some acids. Acids are dangerous chemicals and should be treated with the utmost respect. This unpleasant little critter infects citrus bushes and will squirt an acid in your face if disturbed. The acid is formic acid, the same acid that ants sting you with. Notice the last hydrogen in its structural formula. The element hydrogen is the smallest of all the elements. All acids contain hydrogen. When you are given the name of an acid and asked to write its formula, you first rewrite the name in its proper chemical form. This means a name starting with hydrogen. Acetic acid in vinegar becomes hydrogen acetate. Phosphoric acid, used as a preservative in some soft drinks, becomes hydrogen phosphate. Citric acid crystals, seen here under polarized light, become hydrogen citrate. This chemical is also used as a food acid preservative. Hydrochloric acid is one of the famous strong acids. We convert its name to hydrogen chloride. Use your crossover rules to work out its formula. The valencies are given. We write the two symbols with valencies at the top. We cannot cancel the ones, so we cross them over. Then we rub out the ones to get the final formula, HCl for hydrochloric acid. Sulfuric acid in its concentrated form was known by our forebears as oil of vitriol. This word means that it can burn you horribly. It is made in quantity for use in the steel and detergent industry. It has a terrible passion for water. It rips water molecules out of sugar, paper and human tissue, boiling as it does and leaving a black carbon residue. If you are silly enough to add water to the oil, the water will flash boil up into your face and could blind you. Laboratory assistants are taught to dilute it very slowly by adding acid to water in a fume cupboard. They have to wear protective clothing and goggles to protect themselves. If you accidentally burn yourself with this chemical, you must flood yourself for a long time with water. Sulfuric acid in dilute form is present in car batteries. Unfortunately, some smokestacks also emit the chemical. Your second task is to work out the formula for sulfuric acid using your valence rules. We cross the numbers over, rub out the 1, and do not need to bracket the radical. Nitric acid is banned from sale to the general public, not only for its use in making explosives, but because of serious safety hazards. All the 3 mineral acids studied here emit dangerous gases and in concentrated form should be handled only in fume cupboards. This bottle is labelled nitric acid fuming 100%. The fumes emitted include nitrogen dioxide and the paler dinitrogen tetroxide. These penetrate deep into human lungs, forming nitric acid again. And nitric acid dissolves flesh better than any other acid. All hot fires in the home and spark plugs in our cars emit these gases. The brown haze is more visible in winter, but is paler in summer, but just as deadly. Smog kills thousands in our cities each year, and over 1 million people a year in China as they copy the horrors of Britain's Industrial Revolution. Nitric acid reacts differently to the other 2 acids with metals. The reactions are pretty but dangerous. You may recognise the gas being formed as this copper dissolves in concentrated nitric acid. Your third task now is to work out the formula for nitric acid. The particular chemical hero of this video is Sir Humphrey Davy. Born in the town of Penzance, in the southwestern tip of England, Davy is most celebrated for his invention of the coal miner's safety lamp. By placing gauze on the outside of the lamp flame, Davy was able to spread the heat, preventing the explosion of the deadly methane gas that leaked from the coal seams. The miners called methane fire damp and dreaded it. Davy was a celebrated lecturer, putting on chemical shows for which he charged admission. But his greatest contribution to chemistry was in the use of electricity to extract new unstable chemical elements from their more stable salts. He set up a huge battery of electrical cells in the basement of the Royal Society and used it to isolate the group 7 halogen elements, chlorine and iodine. Using an electrical furnace, he produced the alkaline metals sodium and potassium. He worked further and isolated the alkaline earth metals, magnesium, calcium and barium. We will focus attention on the alkaline metals of group 1. They are all soft and grey with low melting points. Notice that they all have a single electron in their outer shell. They all have valence of +1 because they readily give up their outer electron to other elements or compounds. They do this with water, forming metal hydroxides, which are very, very strong alkalis and will turn phenolphthalein indicator bright pink. The reaction also produces hydrogen gas, which can explode the metal. Your next task is to work out the formulas for the hydroxides of these 4 alkali metals. We cross the numbers over, rub out the 1, and do not need to bracket the radical. Twitchy-nosed experimenters who place no value on their own lungs or eyeballs will be pleased to know that it is possible to burn alkaline metals. Here are 3 of them burning, possibly photographed by someone who is now extinct. Your task is to work out the formulas for the dangerous metal oxide compounds formed as each metal combines with oxygen in the air. The group 1 metals have valence 1 and oxygen has valence 2. We cross the 1 and 2 valence numbers over, then rub out the 1. The old-time chemists discovered some white powdery chemicals that were obviously alkalis as they had a soapy feel and turned indicators their alkaline colours. They named the white powders Beryllia, Magnesia, Lime, Strontia and Baryta. French chemist Antoine Lavoisier suspected that the white powders were compounds, but the French deconstructionist chopped his head off before he could test his idea. It was Humphrey Davy that began extracting the metals from these oxide compounds using electricity. So meet the group 2 elements that we now call alkaline earth metals: beryllium, magnesium, calcium, strontium, barium and radium. 2 of them are vital elements of life. Magnesium is needed by plants to make their green food-making chemical that we call chlorophyll. Calcium is used to make our bone chemicals. The other group 2 elements are quite toxic, particularly the light metal beryllium. All group 2 metals have valence 2 and have 2 electrons in their outer valence shells. Group 2 metals can satisfy their chemical needs by donating their 2 electrons to a group 6 element such as oxygen. Both atoms then have full outer shells of 8 electrons. Alkaline earth metals burn with oxygen spectacularly. The resulting fire is best observed through welders' goggles. Your next task is to write the formulas for these oxides using your formula rules. This time both valencies are 2, so we divide both by 2 before crossing over. Then we rub out the 1s. Although the group 2 metals are not as violently reactive as group 1, they do react with water to produce a metal hydroxide alkali plus hydrogen gas. The reactivity increases down the group. Here white strontium hydroxide forms and bubbles of hydrogen gas rise as strontium is added to water. With calcium a similar reaction occurs, forming calcium hydroxide. This could be carried out by the class, the hydrogen gas trapped and a pulp test done. Test the alkali water formed with phenolphthalein indicator. Wear goggles and do not touch the calcium with wet fingers. Magnesium is a more reluctant reactant, but when hot will react with steam. This equipment is producing steam from wet rock wool. The magnesium reacts in the middle and forms hydrogen gas which has been lit on the right. There is an explosion risk here, so don't try this one. Your task now is to write formulas for the 3 different hydroxides formed. This time the OH radical is bracketed because a 2 is brought down next to it. Metal oxides do not usually survive too long in nature. They tend to combine with the famous greenhouse gas carbon dioxide, forming metal carbonates. One rock that can form is called limestone, which is mostly calcium carbonate. The same chemical in our bones, teeth and in fossils. A more interesting form of limestone is called dolomite, which also contains magnesium carbonate. Gardeners buy this in powdered form. The magnesium keeps their plants green. Your task is to write formulas for the two chemicals in dolomite. Both have valence 2. The 2's cancel out, leaving 1's, which are then rubbed out. The carbonate radical is not bracketed. The salt barium sulfate is a heavy dense chemical. Although poisonous to humans, it is very insoluble in water. Doctors inject it into the human digestive system so that we can X-ray the intestines when we are looking for irregularities. As you can see, humans have a lot of guts. Going to the toilet after this procedure is a whiter than white experience. Work out the formula for a barium sulfate meal or enema. Fireworks have been around since they were invented by Chinese alchemists in the 9th century. The main ingredient is gunpowder, which is a very dangerous mixture, particularly when confined in anything hard. The interesting thing is the chemicals which are added to colour the firework, and you can play with these in the laboratory without any need for explosives. One such colouring chemical is strontium chloride, a white powder. As long as you wear goggles and remember not to scratch them by putting them face down on the bench, you will be quite safe. The Bunsen is clamped sideways to prevent chemical entering the barrel. A loop of nichrome wire is held by a test tube holder. Dip it into strontium chloride solution or powder and hold the loop in the flame with the laboratory lights out. You may clean the wire with water and emery paper and try other salts. Such flame tests for elements was the reason why German Bob Bunsen invented his popular gadget. Your next task is to work out the formula for strontium chloride. The traditional periodic table has two rows of elements cut out of the middle and placed separately at the bottom. These are the lanthanide and actinide elements. When you put them back, the table looks like this. We are focusing on the light red block of elements called the transition metals. Their compounds are very interesting because they are often coloured and the metals often have several valencies. Well, by now your brains are thoroughly trained. We will give you a number of these harder coloured compounds and mark them in groups of 2. If you can do these, you have mastered chemical formulae. To finish up, we might look at a couple of practices that you could do using the transition metal iron. Iron is the main metal used by humans because it is so common in the Earth's crust. Unfortunately, it is a little too reactive, and we spend a lot of time and effort trying to protect it using coatings of zinc, tin, aluminium, or the poisonous red lead oxide. The pracks use goggles. Set up the Bunsen as before with a heat mat under the flame. Ferrum redactum is a fine iron powder. Take a very small pinch and snap your fingers over the flame. You'll notice that iron is used in fireworks. At the end, clean up your mess with a dustpan and brush. The second prac also uses goggles. Make oxygen in a gas jar using manganese dioxide and hydrogen peroxide. Trap the oxygen gas formed using the gas jar lid. Arrange a wad of steel wool loosely on a deflagrating spoon. Ignite the wool on a Bunsen flame and immediately thrust it into the oxygen gas. Look at what is formed. Is it brown iron 3 oxide or blue-grey iron 2 oxide? Write a formula. Science is a great adventure and great fun. Until next time, cheerio.